Hey guys, I just wanted to give you a shorter, more condensed video on these heating and cooling curves and maybe a few heat calculations because you've already seen this information and it was in the Ed puzzle videos, but just in case you wanted to refer back to it, this is going to be just a shorter video and you won't have to watch, 20 minutes worth of a video to get to it. Okay, so this is what we call a heating curve, and it's just a graphical representation of like the phase changes and the changes in energy as an object is heated up, right, their temperature over time. Okay, so I've already got this labeled with a solid, a liquid, and a gas. And side note, this is a heating curve. If you start it up here and bring it down, then it would be called a cooling curve. Okay, so you've got your solid, your liquid, and your gas, right? And as your solid begins changing into a liquid, you are melting. And then you're a liquid for a little while, and then as your liquid changes to your gas, you are vaporizing or evaporating. Okay? But in a cooling curve, if you're going backwards, if you're going this way, gas becoming a liquid is condensation, or condenses, and obviously freezing. Okay, so sorry guys, trying to get my notes together. As you are increasing right here, you see how your temperature is increasing, and temperature is a measure of the average kinetic energy. So we can assume that on this section, this is an increase in kinetic energy. Anywhere you see an increase in temperature, that is measuring an increase in that average kinetic energy. However, as you are going across these phase changes, you are getting a change in your potential energy. Okay, you are increasing the potential energy on these plateaus and increasing the kinetic energy on these, the increasing temperature lines. This is how I remember this. Your 3 P's. Your phase changes and your potential energy all happen on the plateaus. Okay, your 3 P's. So we are going to do some calculations with 3 formulas, and those formulas are appropriate to use at different phases on these heating and cooling curves. Okay, so really quickly though, I want to make sure we understand which phases are endothermic and which ones are exothermic. So I like to show that with particle diagrams. Okay, so if you have solid with your tightly packed particles, your liquids where they are a little bit more energy, a little bit more relaxed, and then your gases, they're everywhere, right? So if you are melting, if you're going from a solid to a liquid, you are increasing your energy. So melting is endothermic. Vaporization is endothermic. Anytime you have an increase in energy, you have an endothermic process. Okay. On the opposite side, if you are thinking of this as a cooling curve, then your gas becoming a liquid and those particles condense in condensation, they have exiting energy, right? Anytime you have a decrease in energy, I think of that as exiting energy. That didn't really make a better mark, but whatever. And those are exothermic processes. Okay? So the 3 formulas that you can use to calculate that heat or that change in your heat are Q equals mass times specific heat times the change in temperature. Okay, and Q is your heat. Q can be positive or negative. If it is positive, it is endothermic, and if it is negative, it is exothermic. Okay, same with your change in temperature. If your temperature increased, if it warmed up, heating curve, then it's positive, and if it's cooling down, it's negative. Okay, the other two formulas, oh, and this is where you have a change in temperature. Okay, so that only is appropriate for the lines that are actually changing in temperature. Q equals MCAT, Q equals MCAT, and Q equals MCAT. Okay, so any line that shows a change in temperature is one where you could calculate Q equals mass times specific heat times change in temperature. And we've learned that specific heat, guys, is just that the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So you have to have a chart for specific heat, right? Like I have to just tell you aluminum specific heat is 0.8 or whatever. Okay, the other two equations you might see are still calculating Q. Okay, so that's still heat. Still needs mass in there. But now we are dealing with what we call the heat of fusion and the heat of vaporization. Okay, heat of fusion is for melting and freezing. Okay, if you have a positive heat of fusion, it's melting, and a negative heat of fusion, it's freezing. Heat of vaporization is up here on the vaporization condensation phase change. So if you have a positive heat of vaporization, it's vaporizing or evaporating, and negative, it's condensing or condensation. Okay, so Q equals these are numbers, heat of fusion and heat of vaporization. So for water, the heat of fusion is 334 joules per gram, and that could be positive or negative, right? If you are melting water, it's positive 334, freezing water, it's negative 334. And heat of vaporization is positive or negative, depending on if you're vaporizing or condensing, 2260. Okay, these are constants, and we will give you those. So these are, I just like this chart so much because it really does give you a great visual of when to use what formula, because there will be times where you're doing a heat calculation and you have to use multiple, steps, because at one step you're going to be increasing in temperature, and then, at this step you're going to melt. Okay, and then you might increase in temperature again. So I'm going to highlight these and these steps. Okay, so let's maybe work a couple of problems in class today. I will also have, obviously, a key to any practice problems, but just in case you needed this chart again, this helps a lot.